our final chapters. So let's get this show on the road. We're going to be looking at hypothesis testing, and this is probably, well, in my opinion, is probably the hardest topic that you're going to meet. So we're going to fight our way through this. There's a lot of structure to hypothesis testing. Essentially, we're going to go through these 4 topics, and I'll talk about them in a few moments. But I want to give you a kind of why do we even need a thing called hypothesis testing? Well, in many sciences, you do experiments or you collect information because you want to prove something is true, right? You have a new idea that you think that this explains better than the old model, or you've come across some interesting information that you believe is true, but it may just be randomness that's going on here. And we, as I was saying to Chris earlier, you aren't allowed, because you've got a vested interest in something being true, you aren't allowed to be the decision maker that this is evidence to prove what I think is true. And because if you resort to, it's my opinion, then you'll always get 22 opinions to any piece of information that you can come up with, right? I think there was an old saying that says if you put 2 economists together, you'd always end up with 3 opinions. So it's not allowed, essentially. Oh, darn it, it's fine. Okay, hold on, sorry. Hello.
Calling to remind you of your upcoming appointment. Donald has an appointment on August 11th, 2021 at 1 p.m. To confirm that you...
I apologize about that. I've got a dental appointment that I wasn't sure when it was going to happen, so they've just told me when it is. So let's pretend I never said the last few minutes, and I'll cut this video up a little bit later. So what we have here is we need a structured way of deciding when you collect data, is this actually proving something, or is it just within the realms of the randomness of collecting information? And that's what hypothesis does. It's a formal way. It takes the person out of the decision. And to be able to set it up, it's kind of been agreed by all scientists, statisticians, the math world, that this is the way to do it. So it's like kind of everybody got together and said, yep, we've all agreed. If you don't do it this way, we're not going to look at your information because we don't know, what you've been up to. And so they're going to be setting up what's called the hypothesis test. That's the first thing we're going to do. That's very formal and very important that we do this precisely. The second stage is we're going to use software, and we're going to use the software, SALT, and we're going to use it to collect what's called a p-value. A p-value is a probability number. It's a very strange number. What we actually find when we find the probability, the p-value, is the probability that your sample happened by luck. And if it's very, very small, and we'll talk about what does very, very small mean, because it's got rules about what number very, very small is. If it's very small, what you can say then is, this data didn't come from randomness. The reason it appeared was because what you thought was true was really true. So it's kind of, you don't look for a big percentage. What you look for is a very small percentage that says what happened wasn't luck. It wasn't randomness in the normal population. It was that small, that unlikely, that it couldn't be randomness. It must be what you thought was true was true. Hope that makes sense. The logic of how you approach it, at least. Now, the third thing is, how do we decide if we have a statistically significant result? Well, once you've found that p-value, there's a little test you do, a little numerical test. And it involves a thing called the significance value, alpha. And then how do you state your conclusions? You state them in a very lawyer-esque way, and then you convert it into English after that. So, 4 main topics on hypothesis tests. Let's start with the first one. How do you set up a hypothesis test? Well, you're going to have some information that is the status quo. Which is, what is the population value meant to be? So an example might be 82% of Americans like football. I made that number up, right? But 82% of Americans like watching football, right? American football. We would write that down. That's called the null hypothesis. This is fancy name. And we write that down as H naught P equals 0.82. All hypothesis tests have 2 hypotheses. Hypothesi, I think you call them, but I'll call them hypotheses. There's a null hypothesis, which is what we used to believe was true. And then you have an alternate. We collected some data, and we think that this percentage has decreased. So we think that it's not 82% anymore. We think less Americans like football for whatever reason. Actually, the 82% is wrong, but do you know that the less is probably true? In the last couple of years, less people have said that they like watching football. I bet you, for instance, that the Olympics will have the same result. Would you agree that the Olympics has probably been less watched this time round than they were the last time? Now, how do we prove that? You can have a gut feeling. Well, you would go out and you collect some data. So they collected some data and they think it. Now, the alternate hypothesis in this case is we think it's decreased. And the alternate hypothesis is called, in this case, P, the population who like watching football, is now less than it used to be. And that is the start of a hypothesis test. You set up the null and alternate hypothesis based on what the story tells you. Now, you normally write them together. So you would write it like this. H naught P equals 0.82. And HA, the alternate, P is less than 0.82. And you'll get questions in your homework where they tell you a story. And then they say to you, write down the null and alternate hypothesis. And when you're being asked to do it, you're going to write these 2 guys down. A couple of things that are kind of truisms. This guy, the null hypothesis, is always P equals, some number. It's always P equals 0.5, 0.82, 0.40, right? And you'll know the null hypothesis because in the story they'll say, we used to believe that 20% of people liked Coca-Cola, or it's a known fact that 50% of Americans have been to Canada, or 20% of people are left-handed, right? They will give you a statement which is kind of, this is the status quo. This is the used to be known truth. And it's always going to be the population p-value is equal to whatever number they say. And then they're going to have, we think it's different now. We think somehow it's changed. And that's going to be the alternate. Now, if you noticed in my story here, the change is that we believe it's reduced. It's got smaller, right? It used to be 82, but now we think it's less. That means, in fact, that there are altogether 3 flavors of hypothesis test. So here's the first one. Let's suppose, different story. This was 75, and we think that it's changed and it's got bigger. That would be one version of a hypothesis test. The status quo, it used to be 32%, but we think it's gone down. It's now less than 32. That is a second version. Can you see that in this story, you're trying to prove evidence that something's got bigger than it used to be? In this one, you're trying to find evidence that something has reduced from what it used to be. This is what it used to be. And lastly, the status quo is it used to be 0.9. Any guesses at what you think the third version of a hypothesis test could be? Could be bigger than the number it used to be. It could be less than the number it used to be. What's left?
Less than or greater to.
Correct, but that's not the way they phrase it. But you're right, it is that. Not equal to. Which is, it could be bigger and it could be less, right? But that's the shorter way of saying that. So these are the 3 versions of hypothesis test. So how will you know which one it is? You read the story. I'm making up stories. 75% of Americans used to go to Canada every year. Totally made up, right? We now think that it's even more. We're going to try and prove it, right? Middle one. 32% of Americans like Coca-Cola. That's what we used to believe. We now think it's less, right? We think people don't like Coca-Cola as much as they used to, right? This one, 90% of Americans, 90% of Americans, what did I make up? Watch TV more than 40 hours a week. We now think that it's different. We're not sure if it's more hours or less hours, but we just know it ain't 90% anymore, right? So 1, 2, and 3. We even have special names for each of these tests. This one here, when you think the evidence is that it's changed and got bigger, that's called a right-tailed test. This one where we think it's got less is called a left-tailed test. And this one where we think it's just different, right? It's not the same as. Any guesses? If you were going to call it a name, what would you call it?
Both tails.
Pretty close. It's called the two-tailed test. And you will find some of your homework questions get you to pick one of those 3. So if, you know, the first part of the question, you've already written this down, then when they ask you what kind of tailed, you're going to call it a left-tailed. And when it's this one, you're going to call it a right-tailed. And when it's this one, you're going to call it a two-tailed. So let me try and show you where those strange names come from, because it's not that obvious why it would be called right or left or whatever. So the theory behind our hypothesis test goes something like this. Let's take this one. We believe that that's true, and we're going to see if there's evidence to prove it's not. Now, if that's true, and you collect a sample, you will create a sampling distribution, won't you? You know, when you pick a sample, it belongs to a sampling distribution. And right in the middle should be that guy. And you get your sample p hat, and your sample, if you're interested in proving is bigger, might be over here somewhere. You see that little shaded area there? That is representing the chances that you got your sample proportion or something bigger. Can you see that that's on the right-hand side? It's right-tailed. And you want that to be tiny, because if that's tiny, it means that this isn't true and the alternate is. Actually, we just phrase it as saying this is true. So when this is so small that it couldn't happen by luck, then it must be because the new alternate hypothesis is correct, right? That P isn't 0.75, it has to be more than that, right? Now, if you did one of these fellas here, the second one, you did a sampling distribution using that number, you'd get 0.32. And then you'd get a p hat, and it's whatever it is. But you'd expect it to be over here, which is there. So far, so good. Now, do you notice that the probability that you get this guy or less is on the left? And that's a left-tailed test. And then for completeness, then the third one, this one. Now, p hat turns up, and it is what it is. But in this world, since we don't even know at the beginning of a hypothesis test what the sample looks like, can you see that as long as it's far away from the middle, and it could be on either side, right? This side or this side, isn't that enough evidence then to prove that it's changed and it's different in some way? And can you see that in this last situation, it might be a big p hat, it might be a very small p hat, but either extreme is good, because either extreme means that that's not true and this is true. And for the same kind of logic, it's going to be two-tailed.
What does the HO and the HA mean?
HO means null hypothesis, and HA means alternate hypothesis.
Oh.
In other textbooks, they're sometimes called H0 and H1. So you might look at a video. H0 is pretty standard. HA is pretty standard, but occasionally a textbook might call it H1. I like HA because at least A stands for alternate. Maybe you're not so happy about H not being a null hypothesis, but it is. That's what we call it. So let's pause a minute and I'll give you a story. Here. And we'll see if we can set up a hypothesis test for it, right? Totally made up data, right? You might not know this, but 40% of Scots adults get drunk on a Saturday. It's just a known fact. 40% of Scotsmen get drunk on a Saturday. We believe that has increased during the COVID, right? So we think even more Scotsmen are getting drunk on Saturday. Now, there'll be more stuff that would happen to this story, but just if we pause at that part, I should be able to set up the null and alternate hypothesis. The null hypothesis is that it's still 40%. What would the alternate hypothesis look like? How would I write down what this story is looking for evidence of?
P greater than 0.4 or 0.4.
Yeah, well, 4. Yeah, 0.4. Do you see that connection? You believe, you want to prove, you think something is valid, whatever way they phrase it. Increased looks like that. Do you see the connection between a story and the null and the alternate? Try another one. 22% of Americans like hamburgers. Okay. We believe that it's been reduced, right? That it's got smaller. Well, the null hypothesis is the 0.22, and we believe that it's got smaller. What name do we give to, what kind of test is this one? What name would we give to this test?
Right tail.
Okay, this one. This is correct. That's a right tail.
That's
What's
left
this one?
tail.
That's a left tail. I won't do the next one, but I'll just say the next one. Could you imagine you had a story where 44% of college students are full-time students, right? They don't have a job as well, right? Just full-time students. And we believe that it's changed. That's it. We believe that it's changed. Can you see in that one, it would be P equals, I think I said 40%, P equals 0.4, and the alternate would be P is not equal to 0.4, right? No reference to it got bigger or smaller, only that it's different or it's changed or it's not the same or whatever. You know, the English language has more than one way to say something, right? But if the gist of it is that it's not what it used to be, right, it's a not equal to. Are we comfortable with that beginning of this process? So I think the way the homework's going to work, or the way I'm going to look at the homework's going to be a little bit different this time, because I'm just going to pick bits of questions that cover what we've talked about, because the questions tend to have a lot of stuff in them, and we don't need to see all of it at once. So I'm looking, I think I'm in 12A. Oh, any questions before we start moving on? I'm going to do some homework questions based on some of this stuff. Okay. Right. Now, while we're in here, we'll get a chance to look at some other things that I've not covered, but they are things that we kind of know, I hope. Right. I don't know which one I just did there. Let me stop this one. Try this again. Come on, Windows, behave. Right, are you looking at 12A testing hypothesis? Okay, I'm in the right place after all. I'll try and make this a little bit bigger. So, question one, the previous example hypothesized that the proportion of babies born during a full
Professor?
moon. Yes.
Do you mean to be showing us the key?
Oh, it's got the key again. Darn it, I wish it would stop doing that. It's more annoying than it's worth. Okay. Yeah, it is distracting to know the answer. It means it's harder for me to tell you, do you know the answer? Okay. So they did a previous one that the proportion of babies born during the full moon is 1 out of 29.53. Evidently, that's the fraction of the year that's full moons, right? Okay. The hypothesis of interest is that the proportion of babies born during the full moon is 1 over 29.5, as it would be the births were equally likely to occur during the full moon as any others. Okay. So that's them basically telling you the null hypothesis. That's it. Right. So, what's the population of interest here?
Portion of babies born during a full moon.
Okay. Let me click that guy on. Do you see it's all babies? The ones born during the full moon are only a subset of all babies born. So the population is everybody, and then we're looking at what fraction of them, right? So if I was doing 55% of Americans like watching football, the population there is all Americans. The ones that like football are just the p-value guys. So now specify the population parameter. Now it's not the same thing as the population. And isn't the population parameter that guy? Right? Which is that one, the bottom one. Okay, null hypothesis. Oh, they give me a fraction button for a change. The H naught is going to be you agree? That's the H naught, the status quo. Okay, they're reading ones. Oh, interesting. Okay, here is, make this bigger. I hope it can stay as letters. Yay. We're going to state a null and alternate hypothesis. And right now they're going to do it using English rather than P equals this number and P is greater than this number, right? So in this story, will an increase in the speed limits on interstate highways lead to an increase in highway fatality rates? So what would the null hypothesis be here? The null hypothesis is that nothing is changed. It's the same as it was before. What's the alternate? The alternate would be fatalities increase. So I'm looking for the combination that says that. I'm going that one. Since it's an increase, it's one-sided. Actually, in this case, it would be a right-tailed. Okay, when a coin is spun on its edge, is the probability that it lands heads up equal to 0.5? So yes, it is null, and it's different if it's not. I believe it's that one. It's also one-sided. Okay, those are a bit weird, but they are there, so I guess I did them. Right, now I've got ones with numbers. Suppose that the present success rate in the treatment of a particular psychiatric disorder from the relevant population is known to be 0.56. So let's say the success rate in treating schizophrenia is 56%, right? A research group hopes to demonstrate that the success rate of a new psychological treatment, maybe it's new drugs, maybe it's a combination of all sorts of things, but this new treatment is better than the standard treatment. Right, now in the standard treatment, P is equal to 0.56. We wanted to find evidence that the new treatment is better than that. So better than that would be greater than 0.56. Are we comfortable with how the null and the alternate, when you've got numbers and real stories, work? I think the two at the top were just far too vague, you know, to be easy to kind of read them. Okay. Now, suppose that a statistic teacher asks his or her students to randomly pick a number from 0 to 7. His general theory is that the proportion who pick the number 0 will be less than those you would expect from just randomness. Use P to represent the population proportion that would pick 0. Now, if things were truly random, wouldn't you agree that there's a 1 out of 8, which is 0.125? And the null hypothesis is that P is equal to 0.125, right? Nothing special going on here, nothing to see. What would the alternate hypothesis be? Because they believes that you will pick 0 less than you'd expect. So how would you describe that in an alternate hypothesis?
HA is less than 0.125.
And we would call that a left-tailed test, or as they say, a one-tailed test, because they're lazy and they don't want to get you to say right or left, I guess. Are we comfortable about how this story becomes null and alternate? You okay with the answer and where the numbers we got came from? Confidence intervals, what we've done, hypothesis testing, which we're about to do, are two of the major ways we do statistical inference, how we prove things. On the basis of this information, do you think that the null and alternate hypothesis are general statements about populations, samples, or both? They're both talking about the entire population. The entire population of Americans who've been to Canada. It's 50% and now it's different, but it's still the entire population in both cases. The fact that you collect a sample is only to try and find evidence to prove something. It doesn't change the fact that it's you're talking about everybody in the population. And this is something you just go through. Another one of these. Well, this one at least has got numbers, so I can do that. An anthropologist is trying to determine if people in a certain region are descended from the same ancestors as those in another region. Okay. So she knows that the region she studied has 19% of the population have a certain unique genetic trait. Right, so when you look at the DNA, they tend to have a certain unusual whatever it is. Now, that very often could simply be they have red hair. Right? It might manifest itself, or they're lactose intolerant, or they have green eyes, you know, all sorts of things that, you know, maybe make that particular group of people kind of common to each other. So that's 19%. And as I carry on with the story, she plans to take a random sample of people in this new region that she thinks are probably the same, related in some way. And she tests them for this trait. If the percentage of the population with this trait in the new region differs from that of the known region, it would indicate that the two populations are actually got different ancestors. Right. So they've got that sentence one, which I don't like, but this one I do. P is equal to 0.91, 19% written down as a decimal. You always do these guys as decimals, never as percentages. Now, in this case, not equal to. You can't really get a not equal to, and I don't know why it wouldn't be that hard to get. So you put exclamation equals to mean not equal to. And the reason I'm doing a not equal to is, in this story, didn't they say if it differs enough from the other one, it means they're not the same ancestry? Right? If they differ in a big enough amount. Here's a candy story. See what that one looks like. Paul likes a certain candy that comes in a bag with mixed colours, each with its own flavour. The candy company website claims that 36% of these candies are red, which is his favourite. He doubts their claim because he's an aficionado on Smarties or M&Ms or whatever they are. And he likes them, and he's noticed that, nah, that it's not 36. I can tell. I've eaten enough bags on it. He thinks it's fewer than 36. Now, the null hypothesis is P equals 0.36. Agreed? Wouldn't it be nice if they had put the alternate box there? Maybe they have, and I've just shrunk it and I can't see it. And there they go, they have. What would the alternate be in Paul's story?
There's less than 35%.
Well, in my case, I think it's 36. So it's the same number, right? But it's either greater than that number, less than that number as it is here, or not equal to that number. Are we good? So far, so good, right? More and more practice. It's a kind of a way of reading something, interpreting it in the language of hypothesis. So this here is the English version of saying it, but this one here is how we would say it normally. So in a last census, so they asked everybody, 9% of school children in a certain state lived with their grandparents. Oh, that's sad. Suppose to support a bill on tax breaks for seniors, a congressional member plans to take a random sample and determines if this percentage is increased. Well, I don't know why they brought in the tax plan, but it doesn't matter. He wants to see, has it increased? That was the part that makes sense to me. So the null hypothesis is that it is 9%. And we want to find out, has it increased? And evidently, they might change the taxes accordingly. Oh, this one just has an H0. I'll skip that one. This one has 2 groups. I don't want that. That's pairs. I don't want that. Okay. Oh, that's not bad. That's as much as I want to do from the homework right now. And let's return back to our usual. Okay. So right now, we have only done one thing. How to find H0 and HA, right? So there's a story, H0, P equals 0.82, alternate, P is less than 0.82, right? That's pretty much all you can do at this point. We're good with that? Right. Now the kind of the major part of this process is, how do you use salt to get this guy called the p-value? Tell you what a p-value is first. Let's suppose that I have a null hypothesis that is 82% of Scotsmen are overweight. And the alternate is that we think that it's been reduced. So the status quo, 82% Scots, adults overweight. And the alternate is that it's reduced. It's gone down. How do we prove that? Right? We think it's true. Maybe, you know, you walk around and you think, yeah, there's not as many fat Scotsmen as there used to be. I think it's reduced. So how do you go about it? Well, you get a sample. Actually, you really should get a simple random sample. But we'll assume that all samples in all questions are simple random samples. And let's suppose you get a simple random sample of 350 Scotsmen. You can imagine that. And there's a number, whatever that number is, it's probably the BMI, isn't it? Is a body mass index. If it's bigger than a certain number, you're overweight, right? So they've got a way of figuring it out. And what they got is P hat. Let me check something out here. And they got 275 for overweight, which happens to be about 0.79. So superficially, would you agree that it's 79% according to our sample? And the population, it used to be 82. Now that is a reduction, agreed? But couldn't you get a random sample of 350 Scotsmen, and every time you do a random sample, isn't this number going to change? Won't sometimes you'll get a lot more fat guys and sometimes a lot less. So there's no guarantee that this particular one is that special. Couldn't it just be one of the random ones that was just a little bit low? Right? And maybe the next time I'll get 85% are overweight, right? And that will be just a random sample that's a little bit in the big side. So we can't use this data to prove anything because it could have came from randomness. So I am getting to salt eventually, but I want to kind of, since we can't do it by hand, I want to try and at least show you the theory behind it. So what we do is we set up a model, and this model is going to create the sampling distribution. Remember the sampling distribution guy? And on our model, let's say here is 0.79. And we find the probability that you get a proportion, right, a p-hat, less than or equal to, in this case, 0.79. And that guy is called the p-value. And then the logic goes like this. If that p-value is so small that it couldn't be just randomness that made this happen, right? It was just too small. Then you can say, you're right, that number is proving that it's got less. But see if this could happen, see if this number here or less could happen, I don't know, 30% of the time. Well, isn't that a pretty big number? That could easily happen lots and lots of times. But suppose it's only 1%, then that would be considered small. In fact, there are 3 levels of how small is small. Right, so how small does this p-value have to be before we've now got evidence that the alternate is true? And here are the 3 values. Oops. 10%, 5%, and 1%. And this is called the 10% significance level. This is called the 5% significance level. And this is called a 1% significance level. And we use a Greek letter of the alphabet. We call this guy alpha. And we almost always write it down as its decimal value. So we would say a significance level alpha of 0.1, a significance level of alpha of 0.5, or a significance level alpha of 0.01. So if you've ever, maybe I don't know if you've ever came across this, but if you ever see some experiment or some result that's been written in a paper and they've done a hypothesis test, they will always say with a significance level of 0.1 or a significance level of 10%. They're telling you this guy when they say that. Now, that's how small you need p-value to be. That guy or smaller, right? So this thing called the p-value, it has to be less than the significance level to be statistically significant. Were you thinking that it had to be much smaller than that before you would have evidence? You thinking, no, this thing here should be like 1 in a million before I could prove something? Well, you know, 1 in a million would be really, really statistically significant, right? But in real life, they are much more generous about how small something needs to be before it's statistically significant. Which should worry you, because if you're doing a significance level of 10%, do you know that that means 10% of the time you will say something is true and it wasn't? It was just randomness that happened to be a little bit in the small side or a little bit in the unlikely side. Now, if you were doing spaceships and people's lives, you can make this significance level much smaller. Couldn't you make it 0.000001? I think that's a million. Because somebody's life might depend on it. And you don't want to risk that. On the other hand, if it's, I think people drink less Coca-Cola than they used to, wouldn't you probably be happy with a 10%? If I think this new medicine does a better job than the old medicine, wouldn't you probably want to make this guy much smaller? You probably want the 1% guy. So the choice of significance level should always be done at the beginning of the story. Don't go looking at the p-value and then decide what your significance level is. Unfortunately, a lot of people do it that way, right? It's peeking at the data. It's one of the nicknames they give that. So you have a look at the data and you say, oh, a p-value of 3%. Okay, I'll make my significance level 5. That way I'll be able to prove something. That's not the way you should be doing it. Before you've even taken your survey or your sample, you should be saying, I'm going to do this hypothesis test and I'm going to live or die by the 1% alpha, a significance level of 1%. And if it don't work out, well, I've wasted some time and money, but I've kept my integrity. I'm not going to change it now. I might choose to do another experiment with even more people in it to see if I can get the evidence I'm looking for. So far, so good. Big picture. This key guy. This is the guy you want. How do we get him? We're going to use Sol. So I need a story from start to finish, and we are going to use that story and do a hypothesis test on it. So here is one I've prepared earlier. The proportion of people in the past in America who have traveled out of state on any given year is 53%. So more than half of Americans in a year will have went from Washington to some other state, right? California, Utah, whatever it is, right? Big chunk. We suspect that that has now been reduced. So we don't think it's 53% anymore. So we collect a random sample of 500 people, and we found out that 250 of them have traveled out of state. Is there enough evidence to prove that there has been a reduction of out-of-state travel using a significance level of alpha equals 0.05? Do you see that story has the whole package, right? It has everything in one place. Now we're going to go through the setting up, and then I'm going to go to Sol and finish it off. I'm essentially going to get the p-value. So the null and alternate hypothesis, they go first. In this story, is it 53% or the p hat, which is this guy here, which is 50%? What number goes next to this one? Is it the 53 as a decimal, or is it the 50% the sample?
53.
Okay. It's the status quo. And we think that there is evidence that it's being reduced. You notice that that doesn't have anything to do with the sample in it. Neither of these numbers are the same number all the time, has anything to do with this guy. This comes later. Now I'm going to go into salt, and hopefully I can do this without too much jumping around. Right, are you looking at salt? Good. Now, really, I just want the salt button. There's a lot of stuff going on here that I don't need. I'm just picking this one out of the way. Oh, darn it in space. Did you notice that I didn't swear there? Did you notice that? Do you see the self-control I've got?
Just do it. You won't touch it.
No. Something's in my head. I got to share it with you. Yeah. If you know anything about me, I come from a huge family. I think it's a huge family. I'm one of 10 children, and the way my family was organised was that my mum and dad had a boy, then they had a whole load of girls, and they had me. And so I was brought up with lots of girls, all looking, watching me, controlling my behaviour, and my dad swore like a trooper. He was a coal miner. I mean, my dad could swear with the best of them, and he did all the usual things that were common there. He was hard drinking, would fight with anything. Really tough man. Swore like a trooper. My mum, I don't think I ever heard. I don't think my mum ever swore in her life. At least I never heard her. And so I picked up all those good habits of not swearing from my mum and my sisters. So I don't. It's not that I don't swear, but I do swear when it's appropriate. So if I hit my thumb with a hammer, I will curse and swear like the best of us. Or if I'm really, really angry, I will swear. But that's very rare. I think swearing is a very useful thing to be able to do. But if you swear all the time, you ever been with people who they just swear like it's part of the English language? They just don't have any way of relieving. You know, if they hit their finger with a hammer, I mean, what do they do? I mean, do they just swear more? I mean, it's not really the same thing. So I think it's good not to swear. I make up words. I say, oh, sugar and bananas and all sorts of things. Right, now, now that I've distracted you totally, let's show you how you do that question in salt. So are you looking at salts? Yeah, okay. I had to do it this way because if I close this window, I'll lose my question, which is a pain in the butt. So hit inferential statistics. Right, so pause on that. Hit inferential statistics. I wonder if I can make that larger because some of you might not have big screens. Right, do you see it there? Now, one sample T, one sample proportion. That's what we're doing right now. So far, so good. One sample proportion. We are using this thing to find this magic guy called the p-value. Remember, that's the magic number we need because he's the guy, if he's really small, is the evidence that we're looking for. So it's phrased as the number of successes. In this story, wasn't it 250 out of 500? Are you comfortable about where I got those numbers from? That's where the sample goes, right? It goes in there, right? 250 out of 500, right? Now, the hypothesis test. I wish Salt had switched these two boxes round, but it is what it is. Our hypothesis test is, the null hypothesis, I should say, is, isn't it P equals 0.53? And isn't the alternate P less than 0.53? Okay, so we are going to use the P less than 0.53. You put the 0.53 here, and then you go over here and you do the less than. Wouldn't it make more sense to me anyway if those boxes were switched? So you pick the less than first and then you can do the 0.53. I mean, I'm just complaining, right? Right, now, you are good to go. Do not hit confidence interval. Just hit this fella. Boom. Do you see null hypothesis, alternate hypothesis, which they're calling H1, but that's fine. Isn't that exactly what it should be? Do you also see a really useful guy? The p-value that I was talking about, yeah? Now, in this case, the p-value, if I round it off, it's 0.09. Are you comfortable about to two decimal places, 0.09? Okay, that's how you get the p-value. Inferential statistics, put in the number of successes out of the total number, right? Put in your sample data essentially. Set up your hypothesis, right? With a p equal to 0.53, greater than, less than, not equal to choice. And then hit generate, and there's your guy. So I'm now going to click back to our original story. And talk about this. Is there enough evidence to prove that there has been a reduction? Well, the test that we use, is the p-value significantly small? Is it less than the significance level? In this case, is 0.09 less than 0.05? Is that a yes or a no? Is the p-value less than that?
No.
It's a big bad no. What that means is then we are really not got enough evidence. I know it's small, but it ain't small enough. Now, can you see the people who might cheat by doing peeking at the data? Once they found that, can you imagine an unscrupulous scientist saying, oh, I was always going to do a 10% significance level? And if they had that, when they came to do this fella, wouldn't you then be able to say yes? Now, you might say, well, it's not really dishonest. He's not, changing the numbers in the sample. Isn't he just changing how small needs to be before I've got significant evidence? But that's not really honest, is it? I mean, changing your choices. So how can you find when someone's doing that? If they're only doing one sample, right, to prove whatever it is they're proving, it's very hard to tell, because maybe they were being totally honest. Maybe they decided it was 10% right before they even went out looking for data. But if they've done 5 or 6 or 7 different things, and you see that it's significant at the 0.1% level on 2 of them, significant at the 0.05 at 2 of them, and significant at the 0.0 level on the last one, isn't that kind of suspicious? Wouldn't you expect they had the same significance level for every one of the 5 situations that they were talking about? So if I read a statistics paper and they tell me things, one of the things I like to look at is what was their significance level. And if it's jumping up and down all over the place, I get a little bit worried. Because I think, he's just cherry picking it to make evidence for all the things. So that's my advice. If you're looking at statistical information and you see that they're jumping around with that significance level. Now, let's pretend we have two different stories so that we can finish this question off. If your p-value is less than the significance level, the answer is no. What does that translate into? This is the sentence that, the formal lawyer sentence that you do. There is not enough evidence to reject. Well, sometimes they just say reject H naught, and sometimes they say it in full, and they say there is not enough evidence to reject the null hypothesis. So that's your standard lawyer sentence to the end of this hypothesis test. There is not enough evidence to reject the null hypothesis. That does not mean that maybe it is different. Maybe it has got smaller. Do you know, all it means is that we haven't been able to prove that it's got smaller. So don't treat this as anything else except we didn't find enough evidence to prove it. That's all it means. You can't then say, then that means the null was always true. No, the null might be false. We just didn't find evidence of it. Analogy. When you do a criminal case, do you notice that the two verdicts are guilty and not guilty? Guilty would be this kind of situation. Yeah, we've proved, that this is true. The alternate is true. And do you know why they say not guilty instead of innocent? Why they phrase it?
Proved not guilty instead of that they totally didn't do it.
Yeah. We don't know that you didn't do it because you never know anything for sure. Don't we just say there's not enough evidence to prove that you did it?
Mm-hmm.
We agree there are people who committed crimes and walked away.
Totally.
Right. So the language that they use in lawyers is very precise language. So the language that we use in hypothesis test is kind of like a lawyer get involved in the job, right? So when we say there's not enough evidence to reject the null, we're not saying that the null is true. We're just saying we don't have any evidence one way or the other. On the other hand, test, is the p-value less than ever? If this had been the original value, right? If we'd made this 10% and this is our yes story, this is the jargon sentence that you do. There is enough evidence to reject the null hypothesis. It's almost the same sentence, right? But instead of there is not enough evidence to reject the null hypothesis, we now say there is enough evidence to reject the null hypothesis. And you might think we finished there, but we don't. We add something else. And so we can conclude that the alternate hypothesis is true. So not only can we prove that there's enough evidence to reject the null hypothesis, since one of them has to be true, if we reject the null, doesn't that also conclude then, the obvious conclusion is that the alternate being the only other choice left must be true. And so when that happens, you've actually proved that less people have traveled out of state. And you could publish that in a paper and other scientists would look at the data and they could check it with their own software and say, oh, you're right. We have evidence then. Now, let's be nitpicky again. Does that guarantee put your money in the bank, spend your entire savings on this being guaranteed true?
No.
No. The significance level is important here because that's the number that we use to decide how small does it need to be before it's not random what you thought was true. It's also a number that tells you how often you get it wrong. If you use a significance level of 5%, as we did here, or in this case, 10%, as we did here, or 1%, which is the other common choice, that significance level is the percentage of the time you're going to get the thing wrong. And by that, I mean, you're going to say there's enough evidence to prove something's true, and it wasn't, right? You know, the guy didn't commit the crime. He was actually innocent. I mean, that does happen as well. Aren't there people who are in jail who didn't commit the crime? It's just the circumstantial evidence was very strong, or people lied and said that they did it and they believed the people, you know, whatever the reason is. That happens as well. So we never say in statistics, this is guaranteed to be true. We just phrase it in, there's enough evidence to say it's true. Right? Which might be nitpicky, but it is important. So don't assume that just because some scientific paper or medical journal or whatever it is has said that we have proved something, don't treat that as like it's guaranteed true. Treat it as the evidence says it's true, and it's very likely to be true. But, you know, it could be one of those really unlucky situations. Now, what reinforces things in the scientific world is that we don't take one person's word for it. See if something happens like a medical treatment and some doctors figured out a more successful way of doing a heart bypass operation. And he's collected data on the survival rate using the old method and his new survival rate using the new method, and it came up as successful, right? And he publishes a paper in the Journal of Heart Disease, and other surgeons are thinking, whoa, that's very interesting. I might want to, you know, learn how his technique works and spend time and effort, you know, doing it. He won't do that yet. What will happen is some surgeons in Canada will try it out, some in Britain will try it out, some in Japan will try it out, and then they will publish follow-up papers. The Japanese said, we did it and we've got the same kind of results, an improvement in success. And the Germans did it and the French did it. And once enough people, like a body of verified different people, you know, with come up with the same conclusion, then it becomes the truth. And hopefully what would happen then is that this new technique would be the new way to do, you know, heart bypass operations. That's essentially how the scientific world works. You prove something and then it gets verified. And once enough people have verified it and it comes out as being exactly the same kind of result as you've got, great. If this person, let's say it's a different story, but let's say this was a medical story again, and he had evidence, and the guy in Japan did it and said, well, I did it and I didn't get any statistical difference at all. And somebody in Japan said, yeah, nothing. And somebody in Germany said nothing. Then what we would say is, oh, we're not saying you lied or you fixed the data. You just got lucky, right? You got, you know, your sample was just a little bit in the big side and that was great, but it wasn't really true. We like that? So we are now going to spend some time using SALT on hypothesis tests. And I'm going to close this fella. And we'll go in. Are you looking at WebAssign homework? Yep. Are you? No? I get a thumbs up, so we are. Okay, so I'm doing 12B right now. So I'm zooming into 12B. Good, can use it. We are being asked here to find p-value. So they haven't given us any story, right? Just to simplify the job, all the numbers that you want and some numbers you don't really need are here. Do you see the null hypothesis?
I can't see
And
it, Professor.
Yeah,
Oh.
there's nothing on your screen.
I didn't swear again, right? I growled, but I didn't swear. Okay, here we go. Can you see it now?
Yes.
Now, I'm going to hit use salt and it's probably going to disappear, but bear with me. I better start writing some numbers down before I do that. So in these questions here, they're telling you the null and the alternate, and we are just going to find the p-value, right? We're not going to do any more than just find p-values. And they tell you the z, which is pointless, but they're telling us it anyway. So what have I got? What are you telling me the Z for? I don't want the Z. Don't want that one. Yeah, I want this one. Yeah. There we go. Right. I don't know why they keep telling me Z scores. I don't need Z scores. I need p-hats. There we go. In this sample, this is question 7. And p-hat is 0.33. And the sample size is 100. And we're told the null hypothesis is p is 0.25. And we're told the alternate hypothesis is p greater than 0.25. When this lesson's finished, I'm going to go back in and kill those early questions with the Z scores. I don't want them. Right, use salt button. Fingers crossed, go. Right, over here, click on it. Are you seeing salt? Right. Can anybody remember which one of these guys along the top that you used to get the p-value?
Inferential statistics.
There we go. Click on one sample, right? Now, number of successes. Well, they told me the p-hat was 0.33 and the n is 100. So if I do a little calculation, is it okay for me to say 33 out of 100 and you're comfortable how I got those two numbers, right, from the 0.33? Because maybe next time it's 0.33 and it's 200 people, right? You'll have to figure out what the success out of the total is. In this case, it's 0.25. And we want a greater than. You comfortable about the greater than and the 0.25? And now I'll generate the results. There's my null, there's my alternate, there's that Z score that I don't care about. And here is my p-value, 0.03 and some stuff. Are we good? Right, move this guy out the way. In here, I would be putting, oops. What did they want the answer to be? 4 decimal places. Well, that's quite accurate. So 0.03233, so 323. Right, the next one, 200 p-hat at 0.54. Right, so p-hat is 0.54. The number is 200, and it's a 75, and it's a less than 75. Okay. Here we go. 0.54 out of 200. How many people is that? 0.54 times 200. That's 108 people out of 200. It's 0.75. And this one they want less than. And then when I hit generate results, we get a p-value, a rather strange result, less than 0.0001. Which means I'm going to have to go 0.0000. In 4 decimal places. If you get a p-value that for all intents and purposes is almost 0, is it that the closest you're probably ever going to get to guaranteeing that it's definitely true? Right? The chances that you get it, wrong would be what p-value is actually measuring would be so small, like 1 in a billion, that's as close as you're ever going to be to being perfect, right? So if you get a p-value that's so darn close to 0 that you can't even write it down virtually, then you know that you're on like bet your house on it and you'll probably be fine, right? It's when you get a p-value of 0.07, shouldn't you be a little bit worried that there's a 7% chance it's screwed up and it might not be true at all? That kind of thing. Move on. Question 8. A certain magazine reported in a survey of 550 randomly selected adult American Catholics that 58% answered the question, do you favor allowing women to be priests? Okay. Now, set the null hypothesis for deciding whether, here's the phrase here, it's very well hidden. More than half of American Catholics favor women being priests, right? Now, do you see a half ends up being this guy? Now, here's a little tip for you. The null hypothesis is always going to be P equals a number, right? It's never going to be greater than or less than, even if the story looks like you're looking for that, it's always equal to. And is there enough evidence that it's greater than 0.5? And I know it's greater than because of that word. Are you comfortable about the null and alternate? We're a little bit less clear than may have been, but that's what they are. The null is always P equals something, and the alternate is P greater than that number, less than that number, or not equal to that number. So far, so good. Now, they have some guys down here that I want to go through, which I haven't covered, but we have covered them before. And they're introducing a funny fella called P naught. Do you see that new guy, P naught? P naught is this fella, the 0.5. They can't call him 0.5 because every question won't that number be different. So they just call it P naught as a placeholder. So if you're going to do a sample, aren't some of the conditions, and we've got them here, right? Have to be true before you can do it. For instance, doesn't that have to be true? Remember NP and N1 minus P have to be bigger than 10. Remember the test? Basically, the sample has to be big enough. They're that same thing in English. Anything else on that list I should be picking?
The randomly select.
Right. Some of these answers are so bad that I don't think you should ever pick them, even by mistake. Can you ever imagine a situation where you picked a sample that was too big? I can't think of one, right? And are there are no, well, come on. Could you only ask one person and base your answer on that? Of course, there's requirements, all right? So the last two are definitely not going to get chosen. Are the conditions met here? Well, if 58% of the sample did say yes, would you agree that's more than 10 people? And if you said 0.5 of 500, would you agree that's plenty? So yes, the samples, everybody's happy. Compute the Z, compute the P. Now that's where we kick in with salt. And we are going to, I'm going to write down the numbers here before I forget. It was 58% of 550. So I'm going to have to figure out how many that ended up being. That ends up being 116 out of 200. Okay, I got that. And the rest I know. Okay, so I'm going to use salt. Bring this guy over. We looking at salt? Yeah, so inferential's already set up, one sample done. I already calculated the 58%, right? The sample, it's 116 out of 200. This guy is 0.5, and we're trying to see, is it greater than, right? Is it more than half? And generate results. And there's that Z statistic that they wanted, right? So you just copy and paste that. And here is the more important value. Here is the P value. So I'm going to copy that. So when I go down here, I'll put in the P value. And if you want 4 decimal places then, so it's 1, 1, that guy. And if you wanted, which you do, the Z statistic, because they asked you for it. I'll put it in here and then just round it off. There we go. Oh, 2 decimal places. There we go. Right. Now, a couple more things, and this question's on. On the basis of the p-value, make a conclusion for a significance test in this situation. Now, somewhere at the top, they should have mentioned something and they didn't, but they did mention it here. Do you see that 0.05 at the end here? You notice that? Isn't that the significance level? 5%. I think they should have mentioned that at the top so that when you come to this part of the question, you say, oh, that's why there's a 0.5 there. Right, now, on this test, right, do you reject or you do not reject the null hypothesis? Right, well, let's look at this p-value. Do you see that guy there? Is he less than 0.05? Agreed, he is. So you reject the null hypothesis. I guess they didn't fill in my entire big sentence because there's maybe not enough room in that drop down to fill it all in without it being really messy. Because the p-value is smaller than 0.05. So far, so good?
I had a question real quick.
Yes.
I'm confused on how you got your Z and your p-value.
Okay, so what I did is I went to salt, which is this guy, and my sample was 58%. So 58% of 200 ended up being 116 out of 200. So what I did is I just found out what 58% of 200 was, and it ended up being 116 people.
Okay.
And then 0.5, because the null hypothesis is it's equal to that, and the alternate hypothesis is it more than 50% of American Catholics want women priests? And so I chose the greater than choice. So this here is another way of saying the alternate is that P is greater than 0.5. And then when you hit generate results, that's where the Z statistics that I got came from. And this is the P value. That's where it came from. And if you look up here, here's the alternate null written down a little bit more formally.
Okay.
And then we finish with, is our p-value less than the significance level, in this case 0.05? And the answer it was, yes it is. And that is done. Now, they have an overlap here with things we've done in the past. We're going to do a 95% confidence interval. And you think, well, how am I going to do that? Well, if I'm in the same place, see if I hit the confidence interval. Right, see a little confidence interval thing? And I make this guy 95%, which is what they want. When I generate the results, can you see the lower limit and the upper limit are there? And so the lower limit was this number. And the upper limit was this number. I'm just doing copying and pasting. And they want it to 3 decimal places. So that guy to 3 decimal places. Are you comfortable how that same place allowed me to get a 95% confidence, and it also allowed me to get a p-value? Just a matter of choosing the right option inside the inference part. Now, this confirms the conclusion. Right, didn't we decide that there was enough evidence to reject the null hypothesis? Would you agree that this confidence interval says that the percentage or proportion of Americans who are in favor of women police, aren't they all bigger than 50? So that confirms what we believe, that more than half Americans, Catholics, believe that. Does that make sense? That the confidence interval wasn't to replace a hypothesis test, it was just a confirmation, right? Yeah, let's look at it from a different point of view. Does it still, is it still agreeing with what I believe to be true? Now, when they do analogy, do you know when there's elections on? Thank God there aren't any right now. But when there is elections on, do you know that very often they tell you who's going to win? Or let's rephrase that. They predict who's going to win. And you wonder how they can do that before even the election has happened. And if you notice anything, they don't always get it right either, don't they? Sometimes say this Democrat's going to win or this Republican's going to win and the other guy ends up winning, right? That can happen as well. But if they do it properly and they do it without any bias, they tend to get it right a lot of the time. One of the quickest ways that they can tell if someone is going to win, let's say it's the whole election, is they do what's called an exit poll. And so when people come out of the polling station, they randomly select people and say, who did you vote for, Republican or Democrat, right? And if they answer it honestly, they can use that sample and then they can test, did more than 50% of the people say they were going to vote Republican? Because isn't that all you need to win the election? More than 50%. And if this was a poll on an election, they can then make a pretty good guesstimate of who's going to win. And I hope they use a significance level of 1%. Because what that will mean is 99% of the time they will get it right. Right? They'll say it's a Republican and he wins, or they say it's a Democrat and he wins. And only 1% of the time they get it wrong. Very often they tend to err on the side of safety. Don't they say things like too close to call, so that they're not committed yet and they wait till maybe later in the day when they've got a lot more information about votes. Cool, this process, isn't it? It takes away bias, because if you collect the sample fairly, we are analysing it, and we will tell you at the end if that's enough evidence to prove what you think is true is in fact true or not. Yeah, we've got time for just one more. So here goes. In the don't want the previous one? Yeah, okay. In the previous example results, I don't know why they phrase it that way. I don't care that they've done it somewhere else, right? Anyway, in a different question, in a survey of students in a stats class who measured the length of their right and left feet. Yeah, I don't believe it. Who knows? Do you know that that is true? That your body is not perfectly symmetric? Olivia, you're nodding like, yeah, I know that my left thumb is 2 millimeters bigger than my right thumb. And nobody else in the right world would be able to be even vaguely interested. But evidently your left feet and your right feet can be different sizes. So I will take the word for it. Now, suppose the right and left foot measures were equal for 109 out of 206 students. So they basically told me my sample, right? It's a 109 out of 206. And if I read further, assume that the class is representative of all college students, is there statistical evidence that the proportion of college students whose feet are the same length differs from a half? Now, the key word here was differ. Not that it's bigger than a half or less than a half, but different, right? Differs from a half. So when we do the null hypothesis, isn't it going to be 0.5? Right.
You're not showing your.
Oh, sorry. Let me go in and share it. Right. Okay. 0.5, right? Differs from a half. Now, what will the alternate look like? Greater than 0.5, less than 0.5, or not equal to 0.5? What does a differ end up becoming?
Not equal to.
Right, and not equal to, we have to do exclamation mark equals. And that isn't exclamation mark equals. That's exclamation mark equals. That's interesting. That looks really ugly. I hope the next generation is salt will just have a not equals to button. Wouldn't that look much better? Because I've got too many equal signs in there, right? Not equals to 0.5. Now, it's talking about verifying the necessary conditions. Would you agree that there's probably more than 10 people said yes and more than 10 people said no? You can look at that data. That's what NP, N1 minus P is about. So we are told that we can assume that the sample is representative in a division. NP naught, the number who said yes, is 109. And N1 minus P naught are the people who said no. So 206 take away 109. 206 take that away 109. And we're looking at 97. Now I can get NP naught and N1 minus P naught two different ways. I just did, oh, that's the people who said yes, so that goes there. If you take that number away from this, that's the people who said no. The other way of doing it is figure out what that is as a decimal and then go 206 times that and you'll get this and then the other value. Now, both quantities are at least 10, which they are. So we found that the necessary conditions are met, okay? That is just testing that you were allowed to do the hypothesis in the first place. Calculate the test statistic. Well, that's interesting. And use technology to find the p-value. Okay, so I'm now going to write down some numbers here, and I've got 109 out of 206, and it's the 0.5, not 0.5 thing. So here we go.
Professor, I typed in the answers
Uh-huh.
for the last part we just did, and it didn't go through. The NP equals,
This fella?
yeah, press enter. I don't think
It-
it'll.
Is your guy the same numbers as mine? Because
Oh,
remember, they
no,
randomize them,
I used my own numbers.
and it didn't agree?
Yeah, mine don't agree either.
Yeah, mine don't either.
Oh, God, it in space. I did the wrong thing. I apologize.
Okay.
I'm now going to. Do you notice it said P not there? Which number is P naught? Isn't it 0.5? I told you that earlier. So, phew, 206 times P naught is 103. And 1 minus P naught is also 103. Because when P naught is 0.5, that's sample size times 0.5. That was my apologies. I did that wrong. It should
I'm
say
sorry.
okay now.
Mine doesn't even like the p-value. And I use my own numbers. Are you dividing the 109 over the 206 to get the proportion?
I'm not doing that yet.
Okay.
So the 0.5 I'm getting is because of we want to check that there's enough evidence that they're different. So different,
That makes sense.
right? So right, I should.
103.
103 was 0.5. P naught's value is 0.5 times the total number of students, which is 206.
Oh, okay. Thanks.
And well, 0.5 is a special case because isn't 1 minus P naught also 0.5? But if one of them was 0.3, the other would be 0.7. So I made a mistake there. Let's hit this fella. And go here. And now I can use the 116. And no, we can't. I'm getting too quick for one good. 116. And number of trials is going to be 200. And the hypothesis is 0.5 because they have no imagination. And wasn't this one, it was different? So it's a not equals to, right? And so I should be able to generate results. And this is my p-value, which I'm going to put here. And can I, darn it, I can't do a check. Can somebody do a check on their guy? Is your p-value coming out okay?
Yes.
Okay, so in my case, the p-value is 2, 3, 4 decimal places. My guy would round up, which would be that one. Now, they've got this fella here called the test statistic. Pretty sure I know who the test statistic is. But I believe it's their name for the Z-score. So something went wonky here, if you can bear with me. Oh, let me show you. There we go. For some reason, this thing updated, maybe found a new question. That guy, not equal to that guy, generate results. So, hey, why is that number different? Because that number's not right. There we go. That was the p-value that worked. I believe this guy is what they're calling the test statistic.
You're right.
Okay. I wish they'd just